All right, hi everybody. Today we're going to go through the first of 3 of our practice problems. Each one's going to cover a different type of idea. The first one is going to be a strong acid, strong base titration. The second one's going to be what happens when one of those 2 things is weak. And the very last one is going to be on calculating an equivalence point. So this first one, we're going to go ahead and let's just hop right in. So the question says, what is the pH when 49 mils of a solution of NaOH has been added to 50 mils of a solution of HCl? Now, first thing I want you to recognize is what are each of these solutions? So NaOH is, of course, going to be our base, and HCl is, of course, going to be our acid. Remember those definitions. So in order to actually do this problem, we're going to start the way we always start, with a balanced chemical equation. When we do this, remember that since this is an acid, it's going to donate a proton, and since this is a base, it's going to accept that proton, and one of our 2 products is definitely going to be water. The other one is going to be a combination of what's left over, so the Cl and the Na is going to make NaCl. That's going to be an aqueous salt that we don't really care about. That's going to be a liquid. Again, we don't really care about that. Are we doing anything with Kas right now? No. Basically, we have to make one major assumption. With a strong acid, I've never used OneNote before, so be patient with me. With a strong acid and base problem, they are going to be molar equivalents. So, in other words, 1 mole of the strong acid will always react with the same exact amount, so 1 mole of the strong base. 1-to-1 reaction. In this particular case, if we were using a strong acid that had 2 protons, maybe things would be a little bit different, but for now, this is what we're sticking with. All right, so now we have our balanced chemical equation, and we've made our first assumption. I'm going to erase some things over here because one of the things that I want to do is I want to get together what looks like an ice table. Now, with an ice table, I want to remind you, the stuff that doesn't matter is going to go, pressing buttons is bad for me. Our strong acid and our strong base are going to be the ones that have molar amounts that matter. Our water and our NaCl are both things we don't really care about, especially since we're trying to get to a pH. pH meaning that we're going to have either H or OH left over in order to get it. Okay, so now we're going to start with our initial information. First, we were given the volume of the acid and the molarity. Recall that volume times molarity will give you moles. So if we take our 0.049 liters, why did I convert it to liters? Give you a second. Pretend like I can hear you guys responding. Because our 49 milliliters is not going to have anything in common with our molarity, because our molarity is in terms of moles per liter. So we're going to take our liters and we're going to multiply by the molarity. The molarity was given as 0.100 moles per liter. Oops, this is the volume of the base. I apologize. Right, because we're dealing with NaOH right now. We want to know how much NaOH we're going to add to how much of the acid, okay? So when we do this math, we're going to get 4.9 times 10 to the negative 3rd moles. And we're going to do the same thing for the acid that we started with. This one we were told is going to have 50 milliliters and a solution strength of 0.100 moles per liter of the acid. This is NaOH. This one's going to become 5.0 times 10 to the negative 3rd moles of HCl. All right. So next thing we're going to do is we're actually going to plug these numbers. Whoops. plug these numbers. These two. Into our ice table. And I'm going to do some fancy movement of stuff, aka I'm going to erase all of this. And I'm just going to put these values in my ice table. So before I erase, I will do that as long as nothing goes wrong. Moles. And this is 5.0 times 10 to the negative third moles. Okay, now I'm going to erase this stuff. Man, I need a trick for this. If anybody knows any tricks. I mean, on my little smart board, I used to be able to go like this. Boop. Nope. Doesn't work here. I'm sorry if I didn't get it all. I tried. All right, so now we've got this ice table and we've got our starting number of moles of each thing. Next thing to do is to remember they're going to react 1 to 1. So however many of these can react with these, that will happen. So our change then is going to be whichever one is smaller to leave behind a 0. So again, our change is going to be whichever one is smaller to leave behind a 0 on one and a number on the other. So when we subtract on this one, we're going to be left with this number of moles of the H. Now, I will remind you that since we don't really care about NaCl, remember you can ignore the Na, remember you can ignore the Cl, and this then would become this, also known as the autoionization of water. And if we have 0.10 times 10 to the negative third moles of H plus left over, this is our equilibrium value. This is good. This is what we're going to use to calculate pH. Now, what's the problem? This is only in moles. We need a total volume here. And remember that over the course of this titration, our total volume was the 49 milliliters plus the 50 milliliters that we started with. So our total volume is then going to be 99 milliliters, which is 0.099 liters. So in calculating the pH at the finish, this is what this is, the finish of the titration for us, we're going to take that 0.10 times 10 to the negative third moles, and we're going to divide it by our total volume in liters, and we're going to get a value of 1.0 times 10 to the negative third molar. Okay, that's our concentration of H+. How do I find a pH from that? I hope you're yelling negative log of the concentration, because that's what you should be doing. When we plug that in, we get a value of 3 molar. So what does this value actually mean? And I'm going to remind you of the table we saw, the pH curves that we were looking at. This would be volume of NaOH because NaOH is what was added. Remember, since this is a strong base, its pH is pretty low. Pretty low, pretty low. Eventually we hit a point where it gets real steep and then it kind of levels off again. And somewhere in here is the equivalence point. And what happens is we're not quite there. We're still about here. This pH of 3, it's not molar. This pH of 3 puts us right about there, right before the equivalence point in that titration curve. All right, so that was part 1 of this question. I'm going to go ahead and move down for part 2. It says to calculate the pH when 51 mils of a 0.1 molar NaOH solution is actually added to a 50 milliliter solution of HCl. So again, I'm going to do some pre-calculating. The first is going to be, since I know I'm going to need it, I'm going to calculate the total volume once they've been added together. Looks like it's going to be 101 milliliters, which is going to be 0.101 liters. Next thing I'm going to do is calculate my molar volume. Remember, the reaction is the same here. So we're going to get this kind of simplified version. We're going to do an ice table. And we're going to remember that in the ice table that the liquid water does not matter. So what we need is the numbers that go in our initial value. All right, so in order to calculate that, just like we did before, I erased things up above. We're going to take the volume in liters multiplied by the molarity of the solution. So for NaOH, this means this, and this is a number of moles, which I'm going to put in my table right away. And then we're going to do the same thing for the HCl. We're staying with the same amount, same strength. So this should be the exact same number we started with in the previous problem. From there, we're going to do the change thing that we did before. Remember, what I told you in the previous problem is we're going to subtract whichever one is smaller from both. So this guy's smaller. Can't subtract this one from both. You'd be left with a negative number. You should never have negative numbers for concentrations. In doing that, this leaves behind a 0. Remember, all of one of them has to react in a strong acid, strong base titration. The other one is going to be the one left over, so this one's going to leave behind that many moles. This number of moles is going to get us the concentration of OH minus at equilibrium, or after the titration. Does it matter that it's not the H plus? No, because we could always do a POH and then subtract from 14, which is what we're going to do. So the concentration of OH after the titration is going to be the total number of moles divided by the volume in liters of the total solution. That's going to give us a value of 1 times 10 to the negative 13, or negative third. The POH is going to be the negative log of that value, which is going to come out to be 3. But the pH is our goal, so we're going to do 14 minus 3, which is going to be 11. That pH, and let's draw ourselves a titration curve real quick. See where we're at. Again, we always put the thing we're adding in the titration on the curve on the bottom. So initially we were here. We saw a steep curve. We were here. Now we're up here. And if you're wondering what I'm referencing as far as like a graph, this is figure 17.8. Or I'm sorry, that's not 17. 17 point, what number? 7. If you want to reference the strong base titrated into the acid is what you're looking at, okay? All right, so in order to show that you've watched this video and you followed along pretty well, I want you to do these problems and submit. That was problem 1.